All right, so we're going to be on example number 6, I think. Or are we on 5? All right, so find the third Taylor polynomial for f of x equal to sine of x expanded about c equal to pi over 6. So notice we are going to do a Taylor polynomial, so not Maclaurin. That means it's not centered at 0. This is centered at pi over 6. They use the word expanded about instead of centered at. It means the same thing, okay? So just to write this out, they want third degree Taylor polynomial, so I'm going to write it out. F of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus f triple prime of c x minus c cubed over 3 factorial. All right, so I write out the general definition because that gives me direction, okay? It tells me the direction I have to go. So first off, I'm going to get my original functions f of x, which is sine of x, and then take a derivative of it. So that'd be cosine of x. Take another derivative of it. That'd be negative sine of x. And take one more derivative of it, negative cosine of x. Remember, third degree means go all the way to third derivative. Now what I'm going to do is plug in my center into those functions. So f of pi over 6 and f prime of pi over 6, f double prime of pi over 6, and f triple prime of pi over 6. Now, sine of pi over 6 is half. Okay? For the next one, cosine of pi over 6 is radical 3 over 2. Then the next one will be a negative half, and the next one will be a negative radical 3 over 2. So those are my coefficients right now. Okay, up on the top where it says f prime, f double prime of c, f triple prime of c, that's what I'm putting up there. Once I have that, I can rewrite this if you want to make it look a little bit more like, okay, here's what we're doing. So p sub 3 of x will be f of pi over 6 plus f prime of pi over 6 times x minus pi over 6 plus f double prime of pi over 6 times x minus pi over 6 squared divided by 2 factorial plus f triple prime of pi over 6 times x minus pi over 6 to the third over 3 factorial. That's basically what I'm doing in this problem. I just got to plug everything in. So let's go ahead and do that. So I'll give you a second real quick in case you're copying the top part down. So what's my f of pi over 6? A half. Plus f prime of pi over 6. We're at 3 over 2 times x minus pi over 6. The next one is f double prime of pi over 6. So that's a negative half. Okay, minus 1/2 times 2 factorial. And then x minus pi over 6 to the third. Oh yes, thank you. Squared. And the last one is f triple prime, so that'd be negative radical 3 over 2 times 3 factorial. Okay, and then x minus pi over 6 to the third. Now you could just leave your answer like that, and that's perfectly fine. There's nothing wrong with it. Okay, if you want to simplify it just a little bit, you'll notice everything has a half in it. Excuse me. So now that everything has a half in it, I take it out, and I can just put 1 plus radical 3 x minus pi over 6 minus 1 over 2 factorial x minus pi over 6 squared minus radical 3 over 3 factorial excuse me, x minus pi over 6 cubed. You could do that if you want to, you don't have to. Now, why would you maybe want to do that? It kind of depends. Maybe there's a question where they want you to simplify something and try to bring out a certain factor or something like that. So maybe simplifying could be helpful. Okay, or maybe it's not. So that's completely up to you how far you want to go. I'm used to breaking it down as much as possible because when you do that, it might be helpful for other work that's coming up. Usually in the AP tests, they do want you to factor as much as you can, because then from there you're supposed to like develop patterns. So by canceling stuff out, factoring, you find patterns that'll help you create other functions. So again, it's up to you if you want to do it or not. Just make sure you know how to factor them if you ever do have to do it. So that's this problem here. Okay, this is the third degree Taylor polynomial for sine of x, centered at pi over 6, centered at 30 degrees. Okay, and they say if you were to graph this function, it would look similar excuse me, it would look similar to your sine of x function. So maybe not perfect, because remember, we're only on the third power. But if you were to go like to 12th power, 18th power, 50th power, it would start matching more and more and more. Okay, remember, we're finding equations, okay, in polynomial form that are supposed to represent like exponentials and trigonometric functions. That's what we're looking for. Okay, exponential ways to represent those functions in a polynomial form. So let me show you the last problem, and then we're done with this section. So example number 7, sorry. So use the fourth degree Maclaurin polynomial to approximate the value of ln of 1.1.
So is this what our calculator does to figure out the values of odd signs?
Well, yeah, like for example, if you wanted to figure out ln of 1.1 on your calculator, you just type it in, right?
Yeah.
They didn't have that back then. So they had to figure out how are we going to do this? How are we going to approximate that value? So they started to create these polynomial expressions, and they found that the more work they put into it, the better their values were. So again, these are called approximations because they're never exact, but they get close. Okay. So remember, if this is a Maclaurin polynomial, that means C has to be what? 0, right? Which means if you write f of x equal to ln of x and you did f of 0, what would happen? What's ln of 0? So we got a problem. Okay? We have to use 0, but it has to be a natural log function. So this is what you do whenever this happens. If you're going to have to use the 0, but you can't plug it in because ln of x doesn't work, then just think of another function just like it that's part of its family. So in other words, let's use ln of x plus 1. Because now if I plug in 0, I get ln of 1, which is 0, right? And that's fine. So if you ever get into that type of problem where like you try to plug in a value and it doesn't work, then just change it just a little bit. Keep it in the same family, okay? Don't go from natural log to like exponential, all right? Keep it as a natural log. Just manipulate it a little bit. So here we go. So what I'm going to do right now is I'm going to use my f of x function here, this new one that we created. And I'm going to take the derivatives of it, okay? So if you guys don't mind, just to save us a little bit of time, I did them beforehand, okay? So this would just be x plus 1 to the negative 1. Second derivative, now they want fourth degree, right? So second derivative is going to be negative x plus 1 to the negative 2. Third derivative is going to be 2 times x plus 1 to the negative 3. And the fourth derivative is going to be negative 6 x plus 1 to the negative 4. Now I'm going to plug in a 0 into all of these. So f of 0, f prime of 0, f double prime of 0, triple prime of 0, and quadruple prime of 0. And here are the answers you should get. 0, 1, negative 1, 2, and negative 6. Right? So once I get all that stuff, I'm going to rewrite the definition of a Maclaurin polynomial, fourth degree. So it's going to be f of 0 plus f prime of 0 x. Actually, it should just be x, not x minus 0, but just x, plus f double prime at 0 x squared over 2 factorial, plus f triple prime at 0 x cubed over 3 factorial, plus f quadruple prime at 0 x to the 4th over 4 factorial. That's the general form for your Maclaurin polynomial. So all I got to do is plug in numbers, and I'm done creating my polynomial. So let's plug in some numbers. So p sub 4 of x would be f of 0 is 0. F prime of 0 is 1, so just x. Plus f double prime, that's minus 1 over 2 factorial x squared. F triple prime is 2, so that'd be 2 over 3 factorial x cubed. And then my last one will be minus 6 over 4 factorial x to the 4th. Right? So I can simplify this a little bit. I can get rid of these factorials. It should be kind of easy. P sub 4 of x is x minus x squared over 2. Are we okay with that? The first one, just 2 factorials, 1 times 2, right? Notice 3 factorial is 3 times 2 times 1. So the 2's will cancel. It's just going to be a 3. So x cubed over 3 minus, and then for my 4 factorial, that's 4 times 3 times 2 times 1. Now notice 3 times 2, that's 6. That's going to cancel with the 6 up on top. So this will be x to the 4th over 4. So are we okay with that? Remember, I'm just going to write it up here because I didn't want to put that in the notes. But this is 4 times 3 times 2 times 1. So this cancels there. Okay. This is 3 times 2 times 1. So that cancels here. Right? That's how those numbers reduced. Okay. So here's my polynomial. Okay. Here's my polynomial. So I'm done. If they were just to have told me create a 4th degree Maclaurin polynomial for the function ln of x, well, I just did it for ln of x plus 1, but it's pretty much the same idea. Okay, it's going to be like this because I can't do x because if I start at 0, then I can't plug in a 0. It doesn't let me. So all I have to do now is my approximation, because that was actually the original problem, right? They said they didn't tell me to create a 4th degree Maclaurin. They said use one. So I had to create one. But now that I've created one, I got to find ln of 1.1, right? Which is basically, they want me to approximate it using my polynomial. So what I'm going to do is just go p, whoops, I don't know what happened there, p sub 4 of 1.1, because this is approximately ln of 1.1. So I just got to plug it in, right? So 1.1, let me just put this right here. So minus squared over 2 plus cubed over 3 minus 4th over 4, right? I'm just plugging in the 1.1s. And I end up getting an approximation of 0.095. Okay, so that's my approximation, 0.095. Now let me just check something really quick.
It nearly matches the value of the calculator.
Yeah, it's almost there, right? It's almost there. So it's close. So you can see, the interesting thing about teaching BC is this. Most of the stuff that you guys learn